This is a tutorial of the Virtual Reference Analyzer by Inometrix. To start the program, click on Start, and then click on the Virtual Reference Analyzer. The front panel on the software is divided into a left side and a right side. On the left, we have pre-scan parameters, or pre-runtime parameters. On the right, we have runtime parameters which we can set. The start-stop wavelength and the output power depend on the particular tunable laser that's used, and we don't limit these values. If you please check the manual for your particular tunable laser to find acceptable ranges for these parameters, as we don't limit their values. On the TLS port, we have a drop-down menu, and you can click refresh to select your tunable laser or the GPIB address of your instrument. The mainframe, whether you're using a legacy A series tunable laser or a B series on the 81600. So this is the mainframes that each uses, and depending on the model of your virtual reference analyzer, you may have more than one channel. If you do, then there's this radial selector for that. Under measurement parameters, this is the number of points desired in the dispersion measurements. So we take the scan range, which will be determined in the range tab, and it's divided into 50 points, 50 evenly distributed points. Now, if during the range, so this number would be decremented if it cannot find a measurement point between 2 points in these 50 points after searching between points 10 times. So if you see this number decrement, that just means that it wasn't able to find a point within that between 2 points in that range. Under configuration, this has several options, and this depends on the configuration of the unbalanced interferometer attached at the DUT port. So Fabry-Perot is our standard way of making measurements. It's basically, we do in reflection, we look at the reflected face fronts from the front and end facets of a fiber under test, for example. This configuration looks exactly mathematically like a Michelson, so the interference pattern produced would be the same. You can also set up the system so that you have a Mach Zender, an unbalanced Mach Zender, where you take you take the light directly from the tunable laser, and the output of the Mach Zender, or the opposite end, is connected to the DUT port. Or you can connect a bulk element in reflection, for example, a fiber Bragg grating to it. So these are the options that we have. Once everything is set up, you can hit scan, and then the laser will sweep. You'll hear a click, the laser will sweep, and you get an interference pattern. I don't have a laser attached, so I can't do that right now. But once you have the raw scan, you can actually save it to a file. It's a generic file. It can be converted to a text if you like. It's really a tab delimited text file that can be opened up in MATLAB, LabVIEW, Notepad, etc. So load, and then there's quit if you want to exit. But I'm going to load a previous scan here. Let's say we use a dispersion compensating fiber. This is negative dispersion as an example. So we load it. We get our interference. This is our interference pattern. These sliders just allow us to select sub bandwidths within our scan. Okay, so we can do that. I'm going to use the full scan here. This doesn't require normalization or filtering, but I'm going to show you anyway. You would require it if you have tones on top of your interference to eliminate their effect. So we're going to just show it. It's not absolutely necessary for most scans to do this, but the functionality is there. If we click on these tabs, then the program automatically advances through the filter and normalize tabs. Otherwise, it skips right to balance and fit. So we'll do that here. So you have your original interference pattern and what the result of filtering. So we can control the filtering here. Um, Now the DC or zero frequency is at 0, but it's mirrored across the 0.5. Okay, this 0.5 of the sampling frequency. So what I'm going to do is I'm going to remove the DC component to show you that there's two peaks here. Now this is where all the information is. It's in the peaks. Now, since it's mirrored, the information it's doubled. We can actually just remove this half because it doesn't change because the information is on this side of the interference pattern of the of the FFT, and I can remove the high frequency without any issue here because all of the dispersion information is in this peak here. Okay, so I can do that. I don't have to do any of this actually, but we're just showing you the functionality. And this is the normalization. So basically, it just takes the interference pattern and scales it so that the results are between -1 and 1. How it does this is here. See this window size here. So it basically takes a moving window of 50 points, and it takes the average of those 50 points, and it uses that value to scale the interference pattern of the 50 points that are around there. So it scales them such that the maximum and minimum is between -1 and 1. So the more points you use, the less fine you're going to have higher frequency on the top of this interference. Anyway, this is just to scale the points. If you like to see it scaled, it's not absolutely necessary in this particular scan. So if we clicked OK, we get to this balance and fit tab. Now there's 3 sub-tabs. There's coarse balance, fine balance, and fit. So what we're doing here is this is a power spectrum of the interference pattern, and we're looking for the most common frequency. Now it's going to have a spread because there's dispersion in the interference pattern, so the frequency or the phase of the interference pattern changes. So we have more than one frequency, but we're looking for the peak. So what we're going to do is we're just going to increase it just slightly. We just want to increase it until we can see the peak. Okay, so let's say we're somewhere in here. We could see a peak, and so basically we've got a peak. If there's more than one peak, let's say you have a cascade of fibers, and you'll have more than one peak. But here we only have one peak, so we're going to reference this first peak, and it's at 2.74 times 10 to the 11 per meter. The frequency, it's in per meter because it's spectral. It's a spectral frequency. So anyway, so that's that. Now we're going to move to the fine balance tab. Now the fine balance tab is for making fine changes in length to the virtual reference path length. Now remember, the virtual reference length, it balances the imbalance, okay, the group delay imbalance in the physical interferometer attached at the DUT port. Okay, so by changing this length, we're effectively balancing the group delay between the arms, so virtually balancing the group delay between the two, between the physical interferometer and the real interferometer. So the imbalance in the physical interferometer is balanced by that in the virtual reference. So here we will increase the length of our virtual reference and bring the balance point. Now the balance point is the center of symmetry here. It's not actually completely symmetric, but we'll call it the center of symmetry here, where this large peak is. Okay. So now we've got our balancing. We're fine balanced here, and we'll move to the next tab where we fit to this interference pattern. So because we can't extract information directly from this, we need to get the phase of the amplitude modulation. So we do a spline fit. Now there are many values that are acceptable for the spline fit. So I mean, there's an acceptable range. The goal here is this. The goal is to have just one peak or one valley point detected for every peak and valley in the interference pattern. Okay, we don't want it to be too high, so if I really raise this too high, then you have multiple peaks and valleys detected because it's trying to fit to this high frequency. So we're basically just extracting the amplitude modulation. Okay, but this still has lots of points on the center, so we want to reduce it. Now, we don't want it to be too low, otherwise we don't get the information. So we want to just be high enough that we can extract the information and have a good contrast for the peaks so that noise doesn't come into the picture. There's no noisy points. There's no mismarked points, basically. Okay, so we're just gonna set this any value, any range, any value should work within these two extremes. You're gonna get good results either way because the information, the dispersion information, is encoded in the separation between peaks. So we need to locate those peaks. Just give you some more information on functionality. You can actually directly input the spline fit parameter. You can directly input the virtual reference length if you click on manually input LV, so you can directly input it there instead of using the technique used here. Now, interpolate spline we don't always often use with if we have a tunable laser connected, because typically we have, well, we can do it if we do FPGs, but anyway, basically we have a million points in this scan, so the resolution on the wavelength location of the peaks is already quite high. If you want it higher, then you just click on interpolate spline and it will interpolate between the points of the spline. It'll do a spline interpolation so that you can better locate the peaks. You have a higher resolution on the location of the peak, wavelength resolution. Okay, so once we've done that, we can click on OK, and it takes us to the range tab. Now, the range tab has some interesting things that we can do. We can the point here is to set the minimum and the maximum length of the virtual reference path, so that this center center of symmetry here is within the scan range. So we want to for the minimum, we want the lowest possible value so that the center, I say center is within the scan range, but we need at least 2 peaks or 2 valleys to be visible in the scan range. And to help you, see this minimum OK? It tells you that we're within, it can make a measurement using this interference pattern. So I'm going to slide it over. Now, if you don't want to do this manually, you just click on Automate Range Measurement, and it will automatically do it, find the range for you. I like to do it manually because I like that control over exactly where the range. I mean, I could start it here. It'll miss some points because I can't make a measurement here, but at least I know that I'm within the maximum. Have a nice range here. So anyway, so we'll leave it like that. We could click on that. Now, what does this accept patterns with noise? Well, if there's more than one point here, it will automatically throw it away. If you want to add some flexibility, reduce the, give the system more flexibility to accept a greater range of interference patterns, you can add that. The reason why it's not added in automatically is that it's a higher constraint. You're only going to accept patterns that have this only one peak on the center. So it just increases the constraint, and it can reduce the scatter depending on your other settings. Okay. Now, what does this stuff? There's some more information down here, more controls down here. You can leave it to the default values, so you can leave this information. Now, to modify this, you have to understand how the system works. Okay, first, include effect of third order dispersion. Well, by default, we include the effect of the third order dispersion in our calculation. What's third order dispersion? Well, it's the asymmetry across the center. Any asymmetry is in this interference pattern is produced by the presence of third order dispersion. If we ignore the effect, so if we include it, our scatter will be slightly higher because of noise in this measurement. So the scatter in our dispersion measurement results can be higher. If we eliminate it, if we ignore this effect, our scatter would be lower. But this can only be ignored when the third order dispersion is low. It is low in SMF28, also in DCF, but some types of fibers don't have low third order dispersion. Okay, so that's one. Now, maximum deviation in the fringe period at the center of the scan range and the edges of the scan range works together with the minimum number of peak or valley points in a calculation. Now, how does this work? Okay, so to make a measurement of dispersion, we're measuring the location of the peak and valley points on the interference pattern. Now, what happens if there's noise here? Like, let's say that a peak is detected between two peaks, or between a peak and a valley. That's noise. That affects our dispersion measurement. So what this maximum deviation means in the fringe period is we're looking at the fringe period and we're looking at the changes in the fringe period. If that change is greater than this value, let's say 1.5, it cuts off everything after so that it doesn't affect the dispersion measurement. Now, why do we have on the sides, or center of scan range versus edges of scan range? Well, look, at the edges of the scan range, when the center is near an edge, you have more high frequency points. So there's more chance of noise, but they're closer together, the periods. So you need to tighten. You can leave them the same. It won't. I mean, if you reduce this, it makes the measurement it'll give you dispersion measurements with lower scatter, because it's cutting off before the frequency starts to get, the tolerance is higher, basically. You have a lower tolerance on changes. So you'll cut off any potential noise by using this lower deviation tolerance. Okay, now what happens? So what's this minimum here? This minimum number of peak valley at 5. So you need to make a dispersion measurement, you need 5 points. You need the center point, and then you need a peak, 2 peaks on each side, or 2 peaks or 2 valleys on each side of this balance point in order to make a dispersion measurement. Okay, so you need 5 points minimum. If you want to increase this, what that means is that, you know how we're cutting off if there's a noise point? Well, there's a potential to have when you cut off, you're using less points to make your dispersion measurement. So if you increase the number of points, you're throwing away those measurements. You're saying we are not going to use those measurements with less than, let's say 5 or let's say 10 points in the calculation. So you're increasing the you're making it more, you're discriminating against those measurements with less points. Okay, so this can give you lower scatter in your measurements, because you're only going to accept those patterns that have a large number of points. So the maximum deviation in the fringe period and the minimum number of points work together. Okay, this sets your tolerance, and this says we will only accept those patterns with more than 5 points, or whatever number you put here. Now, again, the discrimination between the center of the scan and the edges of the scan. Okay, the reason why we make this lower, again, is because at the edges of the scan, you have the points are closer together. Near the center, you're not seeing these short periods, so you can have a higher tolerance. You can tolerate greater deviation. Okay, so I'm going to now press OK, and it's going to advance us to the sweep tab. I could automate the range measurement if I like, but I like to do it manually. It doesn't really make much of a difference. We'll press OK, And the system is now, remember I said, it's dividing it into 50 points. It's measuring at each of those 50 points. If it can't get a measurement, it measures between those points. So now you see we have our group delay, group velocity dispersion, and dispersion length. I wanted to point out something. The independent axis is the group delay. The dependent axis is the wavelength. You'll notice that there are 2 points here where it's shifted. The reason for the shift, this point should be here, but the problem was that the balance point was erroneously detected at this point, okay, because of noise in the interference pattern. So the algorithm used to detect the balance point, that large peak, there was some noise that affected that measurement. So these 2 points would have to be thrown out of the measurement. But you can actually run this scan over and over again. You can reload and change the parameters. You'll get this curve, and you might get some points in here as well. So at the end of the day, you can keep using the same scan to re-verify your measurements. Now I'm going to export the results, and now these results go to let's say I'm going to make a file here. Let's say file, and then I'm going to double click, say open, and I'm going to save my file here as a test results. Okay, now it saves it as a tab delimited file. It's a generic file. What you can do, I'm gonna quit out of here. You can click on it. You can actually change it into a text file if you want Notepad to open it up, right? And there you have your results. Okay, wavelength, group delay, group velocity dispersion, dispersion length. Okay, so there are your results, and you can import them or export them across to MATLAB, LabVIEW, Excel, etc. And you can use the results for whatever you're measuring. Anyway, thank you for taking this tutorial, and we hope you enjoy your new virtual reference analyzer.